Welcome to the 1976 Nobel Prize in Physics. Another one of these shared prizes went between two guys. This one's a little bit different than some of the other shared prizes where people are like in the same lab working on the same project. This one's a little weirder. So, what do I mean? Let's explain. This one went to Burton, Richter, and Sam Ting for the discovery of what is called the J psi particle. Why does it have two names? We'll get to that. What happened was some guys at Stanford and some guys at MIT were all working in particle physics, and they came across something and they kind of went, "Well, that's pretty cool. It's kind of interesting." And it turned out to be the same discovery gotten to by two different methods, which is even cooler because that's kind of exactly what you want. There shouldn't be one explicit way to, ooh, do this and this and this, and that's the only way you'll ever see this, right? It should be able to be done in a variety of ways. It turns out the J particle is one of those things. I'm going to call it the J particle because I've actually met Professor Ting, and I actually ran some experiments, collaborated on some experiments in the same building he used to work in when he made the discovery. So I'm going to call it the J particle. But basically, they both did this around the same time. They were looking at their data. They called each other, or so the story goes, and said, "Hey, look, I found some really interesting stuff. Maybe we should talk about it." They met at Slack in November of I think it was 1974, and they went, "Yep, we're looking at exactly the same thing. How'd you get it? How'd you get it? What's it mean?" And then, of course, they dove in and started to try to explain it. But let's look at the two different methods, and then we'll understand why the J particle was so important and still to this day is. So let's go. So Professor Richter, he led a team at Stanford, and basically they were using a ring type accelerator. So you get particles going around and around and around in a circle. And what he did was he was sending electrons in one direction and positrons in another. And in theory, if you get a head-on collision and they're going exactly the same speed in both directions, you could kind of get them to stand still as they hit each other. So they have the same mass, go bam, poof, and they annihilate. So the idea was they had this apparatus that they could actually get collisions to more than 1,000 energy settings, so 1,000 different speeds going each direction. And when you get the right speed, you get a large number of collisions, and poof, the new particle that they called psi appeared. And there were a lot of surprises about it because they didn't quite expect that large of a particle. It's sort of 3 times the size of a proton, and it lived 1,000 times longer than it really should have. So they were kind of like, well, that's weird. What the heck is this thing? So they decided to start calling people, and one of the people they were decided to talk to was Sam Ting's group over at MIT, who was known for finding new particles all the time. He was sort of one of the world leaders in that. So he said, let me go home and think about this, and I'll go talk to my buddy. Hold on a minute. Now let's go look at what Professor Ting was doing. Okay, so Professor Ting, what he was doing was pretty cool. He was basically taking high-speed protons and setting them on a collision course with a piece of beryllium that was just sitting still. And what happens is a large number of particles start coming out with a bunch of decay products. And they'd spent a long time doing these sort of experiments. We're like, oh my gosh, look at all these things. Let's go figure out what they all are. And they were writing papers and discovering new particles. It was really cool. And this was sort of the way they worked. And then inside one of those sets of data was something that didn't quite fit with what they were expecting. And it turned out was this new particle called the J particle, which now it's referred to as the J psi. It's the same thing. And what he did was he went, holy crap, let me go check this out. So he got on the phone with his buddy out at Stanford. He got on a plane. He flew out there. And they realized they were looking at exactly the same thing. So it was pretty cool that two different groups got there by two different methods, which I thought was pretty neat. Now let's go see, who cares? It's just a particle, right? It's another one of these things in physics labs everybody uses. Who cares? What's it good for? Well, there's more to this little booger. So let's dig in a little bit deeper. So one of the importance of the J particle, there's many of them, but one of the things I want you to remember is this project was done less than 50 years ago. This was done in my lifetime, right? I mean, I was a kid, but it was done in my lifetime. Now, there was a time in history that was not that long ago. We thought the atom was the smallest thing, and then we split that apart. Now come the proton, the neutron, the electron, and then we're like, surely that's the smallest thing that's in there. And then we went, well, okay, maybe not, because we started splitting those apart. Now came the quark. Now, when they discovered the J particle, what they found was it consisted of a type of quark that had never been seen before. They call it the charm quark. And a J particle is actually a charm and an anti-charm kind of stuck together for a while. I mean, they do fall apart pretty fast, but in the large grand scheme of things, but not long enough so that you can't measure it. And what this did was it led to a rapid sort of evolution in our understanding of particle physics, which primarily in the case of the J particle deals with the strong nuclear force. And the more we understand about the strong nuclear force, the better. The other thing it did was it was proof finally that the quark model was actually correct, because up until then people thought it could be real, it could be just this mathematical construct, because a lot of times you try to explain stuff, you come up with math and you're like, well, okay, we'll just think of it as three particles and think of it like this and think of it like that. And it turns out you can kind of convince yourself that the math equates to nature, but nature doesn't care about your math. It cares about what it wants to do. So this project actually kind of solidified that quark model as to being real. Now, is quark the smallest thing, or can we split that apart someday and find something smaller? I don't know. Maybe we will. Who cares? Who knows? Now, but the other thing this did was that this particle really, and I can't stress this enough, permitted an in-depth study of the nuclear strong force. And the more we understand about that nuclear strong force, the more we can possibly understand about how to control nuclear reactions. The more we control nuclear reactions, the more we can control how things work in power plants. And more importantly, maybe someday we can get to fusion and have that work, which is a whole nother subject, which is a pretty cool subject, by the way. I love nuclear fusion. And it was all thanks to all this new understanding, all these new discoveries, all these, hey, let's find more big particles and understand that nuclear strong force. And by the way, here's this new quark you never knew you saw, or you never knew existed. Was all thanks to this little particle. It's so, I mean, it's about 3.5 times the size of a single proton. So we're not talking big. We're talking a tiny little guy that lives for a mere fraction of a second, but gave us such a new understanding of the world down at that scale that it was worthy of a Nobel Prize. So the J particle's it. Professor Richter has passed away. Professor Ting is still with us. He's still kicking around. I don't think he's working anymore. I think he might still come in the lab on occasion. But the what you see here is a cyclotron that was in the same building. Actually, got the privilege to run some experiments in the room that thing is in, or was in. And I put it up there for no other reason other than it's a cool looking piece of equipment. So I hope everybody has enjoyed this video, and we will see you on the next one, which is 1977, which is another cool one. See you then.